Okay. So, let us come back to the power system stability. Actually, in the previous example, when I was telling that delta 1 is 50 degree, I forgot to mention one thing, that this is a non-linear equation and one has to solve iteratively, but for the classroom purpose you have to try little bit trial and error, and that is why delta 1 is approximately your 50 degree. So, this I missed it, I forgot to tell you. So, this is a non-linear equation, right. So, next is that your critical clearing angle and critical your clearing time. So, critical clearing angle and critical clearing time. Before saying that, again we have to little bit brush up our memories, that for equal area criterion I told you that suddenly that there is an input power P I is increased from this value to your this value. At that time your from A to D. So, P I at that time your input power is more than the electrical power. So, in that case the rotor will accelerate and it will move along this path P is equal to P max sin delta B delta sin P max sin delta, and finally, and at this time that rotor it will store kinetic energy, right. So, so in that case it will come to point B, but at this point of course accelerating power is 0, because P A is equal to P I minus P E, but at this point that rotor is running above synchronous speed. So, what will happen, that again it will decelerate that your what you call it will pass point B, and energy will be your whatever energy stored during acceleration, same energy it will release during decelerating condition, and it will move up to C where it attains synchronous speed. Then again at this point that electrical power is more than your what you call that your mechanical power input. So, finally, the rotor will oscillate your what you call around your point B back and forth at its natural frequency, and then machine has its own damping and it will subside these oscillations. Finally, it will be settled at point B. This is that your philosophy of equal area criterion. That means, accelerating energy, that is the area A 1 must be equal to the decelerating energy, that is area A 2, that we have seen. This is to just brush up our memories, just we make it like this. So, now same philosophy will be applied, for example, the critical clearing angle and critical clearing time. So, suppose if a fault occurs in a system, the delta will increase, and under the influence of positive accelerating your power, and the system will become unstable if delta becomes very large. That means, there is a critical angle within which the fault must be cleared if the system is to remain stable and the equal area criterion is to be satisfied. Actually, this angle is known as the critical clearing angle. Then you have an angle, right, up to which your system can I mean if you clear the fault within that value, I mean within that limit, then your system will remain stable. So, for example, suppose you consider this one, just we are considering a single machine infinite bus system. This is infinite bus and input power is P I for the generator, and this is one transmission line, you have another radial transmission line here. Now, you assume that there is a fault at bus F. So, if there is a fault at bus F, so what will happen, that the terminal voltage, the generator terminal voltage will be immediately 0. If it is 0, then immediately generator will not generate any power. So, I repeat that this is another radial transmission line and there is a 3-phase fault say. So, as soon as there is a fault here, the terminal voltage this will be 0 till that line is disconnected, circuit breaker trips, right. As soon as it isolate this your after when that fault is cleared, suppose this line is isolated, that we will see. But question is that if your fault has occurred, then immediately the terminal voltage will become 0, that means generator will not deliver any power. So, power delivered by the generator will be 0. Then that is why you consider this figure 9 for our understanding. First, before saying anything, this is area A1, this is area A2. Now, you assume that figure 9 operating with mechanical input Pi, this is our mechanical input power Pi, and the operating point, the machine was operating at steady state. At that time the angle was delta 0. That means, at that time Pi is equal to P max sin delta. If you put delta is equal to delta 0 here, at that time Pi is equal to P max sin delta 0. This is the steady state operating point. Now, if a 3-phase short circuit occurs at the point A, I told you that at the point A, if 3-phase short circuit occurs here. So, in that case the your that is the outgoing your on the power. Now, if a 3-phase short circuit occurs at the outgoing radial line, I mean this is another line, this is another radial transmission line. So, the terminal voltage goes to 0, that means terminal voltage here will become 0, because fault has occurred here at this point, and hence the electrical power output of the generator instantly reduces to 0, because this voltage is 0. So, already this generator will not deliver any power, that means electrical power is 0, and the state point from A directly it will come to point B, because power is 0. So, if it is so, that means that Pi in general greater than your P, because P has become 0. So, in that case what will happen, that acceleration area A1, this is the acceleration area, will start to increase. So, we will start to, that is acceleration area here this one will start to increase, while the your state point moves along B C. So, this is B to C, I have made this way arrow, and arrow is upward. So, this will start from point B to point C. Suppose at time T C, corresponding to that your clearing angle, this is delta C, at this time the fault is cleared by the opening of the circuit breaker. So, this fault is cleared this circuit breaker by opening of this circuit breaker. So, as soon as this circuit breaker opens, right. So, what will happen, that immediately this is the operating point B to C. So, that means the line will become this line will transmit power, this line will transmit power. So, line will become healthy. So, at that time that it is your what you call at times T C, corresponding clearing time, this is clearing angle delta C, the fault is cleared by opening of the line circuit breaker. T C is called the clearing time, and delta C is called clearing angle. So, delta C is the clearing angle, and the time at which it is cleared, it is called your clearing time. Now, after the fault is cleared, the system again becomes healthy and transmit power P max. P is equal to, this is the sine curve, that P is equal to P max sin delta. So, at this point C, the fault is cleared. So, immediately this point will move to D. So, at that time, right, at that time that your and this point this P at this point, that is the P value, electrical power value is more than that Pi. So, in that case now rotor will decelerate, it will decelerate. So, it will decelerate till the point E, with the same philosophy for equal area criterion, that when area A1 will become area A2, because A2 will begin to increase till the point E, and when A1 will become A2. So, therefore, that if area A1 becomes your area A2, then for stability that clearing angle delta C must be such that this area 1 is equal to area A2. That means, this area, this is actually rectangle, this is actually rectangle. So, it is height is Pi and difference width is delta C minus delta 0. So, this area is Pi into delta C minus delta 0, that is area A1, that is area A1 is equal to your area 2. So, it will be delta C to delta 1, integration delta C to delta 1, then P minus Pi, this is the P max, this is the P curve minus this horizontal line Pi. So, P minus P I. So, if you your what you call that integrate this one, if you integrate this one from this to this, then ultimately you will get the relationship after this thing P max into cosine delta C minus cosine delta 1 is equal to P I into delta 1 minus delta 0 upon simplification. This is equation say 47. Now, at delta is equal to delta 0, right, then P I, that your what you call P I will be is equal to P max sine delta 0 at delta is equal to delta 0. That means P I is equal to P max sine delta 0. We can write, therefore, in this equation you put P I is equal to P max sine delta 0 in this equation here. That means, we are writing that equation your what you call from equation using equation 47 and 48, you put this value here, you put it here, then you will get that cosine delta C is equal to cosine delta 1 plus delta 1 minus delta 0 into sine delta 0. This is equation 49, and delta 1 is that maximum one, it has gone up to this E, and from this figure everything is given. So, it is understandable. So, that means, in order to determine the critical clearing time, we write equation 20 with P is equal to 0. So, if you see equation 20, it is d square delta dt square is equal to pi f upon h in bracket P I minus P, that is equation 20. I am not showing it, it is understandable, but when that your with P is equal to 0, because we have a 3 phase fault, if we have P is equal to 0, therefore, d square delta dt square we can write pi f upon h into P I. In equation 20 you put P is equal to 0. Now, if you integrate this equation twice and if you utilize the fact that at t is equal to 0, d delta by dt is equal to 0, it will give you this one. I ask you to do this integration, right. I am not showing it, but you just take two integration, put all the initial condition from your intuition, and then you will find this expression. So, you should do this. So, I am putting delta is equal to then pi f into P I upon 2 h into t square plus delta 0. This is equation 51. Now, if t is equal to T c say is a clearing time corresponding to a clearing angle delta is equal to delta c, then equation 51 you can write, that means, in this equation you put delta is equal to delta c and t is equal to T c, then you will get the T c value, delta c value as well as T c value. That means if you make it, then this one, the delta c is equal to your, then is equal to pi f P I upon 2 h, then your T c square plus delta 0. From this equation, T c is equal to square root of 2 h into delta c minus delta 0 divided by pi f P I. This is equation 52, right. This is the clearing time. Now, suppose we want to find out what will be the maximum value of your delta c, that is the critical clearing angle. So, that is from this delta c can be obtained from your equation 49. That means, just now we have given 49. From this equation, that cosine delta c is equal to this, cosine delta c is equal to your this one, this equation. From this equation, delta c can be obtained, that is equation 49. Now, as the clearing of the faulty line is delayed, that means, if we delay that faulty line, that your clearing time, then A 1 increases, this A 1 will increase, and so does delta 1, because delta 1 also will increase to find area A 1 is equal to A 2. Now, we are, I mean, if the fault angle delayed, but one thing is there will be a limit, beyond that system will become unstable. So, still A 1 is equal to A 2, if this is the condition. So, in that case delta 1 will become delta m, that means, your this delta 1 finally it will come to a, because delta 1 will come to a value delta m, that is the maximum. So, that is why delta 1 will be, this delta m is equal to actually delta max, the maximum one. That means, if the your what you call clearing of the faulty line is delayed. So, this is the maximum that we can get. That means, my delta m, this is pi, this is pi, that means delta m is equal to pi minus delta 0, this is delta m. So, for a clearing angle or clearing time larger than this value, the system will become unstable, because you cannot get beyond that. So, system will become unstable. That means, the maximum that the system would be the maximum allowable value of the clearing angle and clearing time for the system to remain stable are known as critical clearing angle and critical clearing time. That means, this is the your what you call, that is that maximum that you can get, that is it is called delta critical or what you call that critical clearing angle, and corresponding time we give the TCR, we call your critical clearing time. So, that is why I am putting it here, that the maximum allowable value of the clearing angle and the clearing time of the system to remain system stable are known as critical clearing angle or critical clearing time. This is the maximum allowable value, beyond that system will become unstable. So, from figure from this figure only, from figure 11, this is figure 11, from figure 11 the delta m is equal to pi minus delta, this is pi. So, pi minus delta 0. So, if you substitute into equation 49 this one, just let me find out that in this equation, if you in this equation if you put like this, that your delta m is equal to pi minus delta 0. Actually, delta 1, there should not be any confusion. Actually, this is delta 1 is equal to delta m, and delta m is equal to your pi minus delta 0. So, in this equation you put like this, actually delta 1 is equal to delta m and delta m is equal to, because delta 1 maximum it can come up that delta 1 is equal to delta m, this is the allowable angle, right. So, that means, here if you have any, there should not be any confusion. So, delta 1 is equal to delta m, and in this equation you put delta 1 is equal to delta m, and here also, and then delta m is equal, this one is equal to pi minus delta 0. So, if you put here delta 1 is equal to delta m is equal to pi minus delta 0, then you will get cosine delta CR. First, that is why I am first putting for your understanding, putting delta 1 is equal to delta m from this figure. This is the maximum allowable angle for delta 1, delta 1 is equal to delta m from figure 11 here. So, that means cos delta CR is equal to cos delta m plus delta m minus delta 0 sin delta 0. That equation your 49, we are putting delta 1 is equal to delta m, and then delta m is equal to pi minus delta 0. Now, you put pi minus delta 0, you will get cosine delta CR is equal to in bracket pi minus 2 delta 0 bracket close into sin delta 0 minus cosine delta 0. This is equation 53. So, that is how one will get that your one can find out if delta 0 is known to you, you can compute delta CR, right, critical clearing angle. So, using equation 52, using equation 52, that means this equation that Tc is equal to root over 2 h into delta c minus delta 0 upon pi f pi. Here you put that instead of Tc, Tcr, and instead of delta c, delta Cr, then you will get critical clearing time. So, in this equation, just in place of Tc you put Tcr, and in place of delta c you put delta Cr. So, if you do so, then you will get Tcr is equal to square root of 2 h in bracket delta Cr minus delta 0 divided by pi f into pi. This is equation 54, and delta Cr can be computed that as equation given in equation 53. This you know. So, this is how one can compute the critical clearing time. This is of course, your approximate thing, but this is a good exercise using equal error criterion. Now, next one is little bit we have to understand. So, for suppose next one is we have a double circuit line. Before saying this time, just see we have a double circuit line. So, this is double circuit line, it is single machine infinite bus, of course, this is generator. Multi machine system, here we cannot study, it is a very lengthy procedure, and for multi machine system one has to go for iterative techniques. So, we will not do that, only for undergraduate and for general idea for undergraduate student, as well as those who are I mean have passed out engineering, for them it will be helpful this single machine infinite bus system. So, this is a transformer in any way. So, this is bus 1, bus 2, this is a double circuit line, and suppose a fault has occurred, some mark I have made 1, 2, another bus somehow I have marked 3, but not necessary for this analysis. Suppose a fault has occurred which is little bit away from the substation, from this bus 1, this fault is little bit away, that means as soon as fault has occurred, that it will offer some your although your equivalent this thing what you call the impedance, or if resistance is neglected, so we say reactance, it will increase. But anyway, a fault has occurred, 3 phase fault at a distance or this thing at some distance from the bus 1. So, this is figure 2, the double circuit transmission line, a fault has occurred. Now, this one now consider the fault location at F. I told you this is the fault location at F, it is at some distance from bus 1. So, and this side is the sending end, this is sending end, of course, you know this, and this is receiving end. So, assume that the input power P I, look at this graph, input power P I, this horizontal line is constant, and the machine was operating steadily and delivering power to the system with an power angle delta 0. This is delta 0, and it was your what you call delivering power, and it is shown in figure, that be shown in figure 13. That means, this green curve actually this is called curve A, right. This is before fault, that means pre fault, this is before fault. So, this is your graph A, this is I have marked as A. Now, power angle curve corresponding to the pre fault condition is given curve A. So, this is your curve A, the green one. Now, as the fault location with fault location F at your from the sending end, a little bit away from the sending end, this is little not at the sending end, it is away from the sending end, this fault location. The equivalent transfer reactance between bus bar is increased. That means, this we will see through an example later on, that equivalent transfer your reactance will increase, because it is away from this bus, right. So, in that case what will happen, reactance has increased, and we know power transfer is equal to in general V 1 V 2 upon x sin delta. If x increases, then naturally power transfer will decrease. So, that means, the power transfer capability and the power angle curve is represented by curve B. So, as soon as there is a fault, so during fault, this graph B, this is actually during fault, right, and suddenly the power transfer capability has decreased. So, that is why this that means, initially it was operating at point A, but now suddenly this has your what you call has come to graph B. This is actually during fault. So, during pre fault, during fault and post fault, later we will see the 3 condition. So, in that case what will happen, that as soon as it is falling here, as soon as it is falling to this, that means, this point will be shifting to B, but it will never be 0, because it is double circuit line and fault has occurred away from the substation. It transfer reactance will increase to some extent, and naturally that this curve will be the black one, this black one, and this will be your curve B. This is during fault, I have written here, this graph is during fault. So, from A, the point will be shifting to B. So, as soon as it is coming from here, so that means mechanical input power will be greater than during fault, greater than this electrical power, because this point B is below point A. So, at that time what will happen, means this delta 1, this is the initial operating angle. So, delta this angle delta 1 will be your continuously increasing. So, so in that case what will happen, this is your machine will Pi greater than P because this is during fault. So, machine will accelerate. So, it will store kinetic energy during acceleration, and after some time say at delta is equal to delta 1, the fault is clear and line is isolated. That means, this fault is clear and this line is isolated. So, as soon as it will be single line, it is isolated, its power transfer capability will increase. So, in that case this is the your graph C, the blue one, this is your after fault or post fault, right. This is, that means that your initially it was at A, now a fault has occurred during fault, that power transfer capability has decreased. So, this graph is the black one, it has come to this point, that means A has come to B. Now, Pi is greater than your this mechanical power, this Pi, this is greater than your input power is greater than this electrical power. So, rotor will be accelerating. So, it will store kinetic energy, and delta also, this angle delta, this is delta 1, it continuously increase. So, at some point that fault is cleared, that means this fault is cleared and line is isolated, this line is isolated, it is not there. It is not there, the post fault condition or after fault condition only 1 to 2 this line is there, this is not there. So, in that case that graph, this figure, this single line now. So, your this power graph will be that graph C, that is after fault, and this delta, this point that your from your as it is moving from B to C, delta 1 is increasing on this graph, it was moving B to C, but at delta 1 the fault is cleared. So, it will immediately jump to that point, that after fault, and this sine curve will come, and this is rotor has your stored kinetic energy during acceleration. So, after that what will happen, this it will be decelerating, same philosophy as equal area criterion. So, finally, it will reach to this point F, where your accelerating energy A 1 is equal to decelerating energy A 2, and after that as your this one, this electrical power here on the blue graph at point F, it is greater than Pi. So, basically rotor will oscillate back and forth, that is your this point, at this point, right. This E point is there around this point here. So, it will oscillate at your in back and forth, and finally, that intersection of this, look at this blue line, I have made it Pi, and this is also blue line. So, wherever it will come, this will be your this steady state. I have not marked here by dot or anything, but this will be final steady state, your operating point. Here if you want, here something, I mean this point, it will, because rotor will oscillate back and forth, and finally, it will be settled at this point, because power was Pi, input power was Pi. So, somewhere on the blue graph, not the green one, blue one, it will be settled after oscillating, and the rotor will oscillate actually at its natural frequency, and then the machine has the damping. So, because of its own this damping effect, it will subside the your that rotor oscillation. So, finally, it will settle on this here. Later we will take an example, at that time we will mark this angle by delta m dash. So, this is the philosophy for your for a double circuit your transmission line, single machine infinite bus case, that area 1 must be equal to area 2, and this philosophy same as equal area criterion, here also equal area criterion. So, all these things your all these things I have shown in this black your green one before fault, black one during fault, and this one after fault. So, hope this will be there will be no difficulty at all. Philosophy will remain same as equal area criterion. So, rest whatever I said, that everything is written here, right. So, power angle curve corresponding to the pre-fault condition is given by A, this is this one. Then when with fault location and F away from the sending end, I told you that transfer reactance will increase. So, that is represented by curve B, this is curve B, this is during fault, and when fault is cleared, That means, when single line is operating, this is this is isolated, only this line is there. So, in that case this blue curve is the your power angle curve. So, all these things written here, whatever I said. So, I hope when you will read it, so you pause it and read it, whatever I said, everything is mentioned here. So, that means, if these two area I mean if A1 is equal to A2, if these two area equal, then we will find out all the your this thing your clearing angle and everything. So, everything is written here, whatever I have told. Look at this paragraph, since P is still greater than Pi, the rotor continues to decelerate and the path is retraced along the power angle curve passing through E. I told you that this is along the retraced along the path passing through E, right, to this point E here, right. So, rotor angle will then oscillate back and forth around E at its natural frequency. So, it will oscillate around E at its natural frequency. And finally, the damping presented in the machine will cause this oscillation to subside and a new steady state operation will be established at the intersection of Pi and curve C. I told you, and the intersection of this Pi, the blue one, and this blue curve, this will be your what you call the steady state operating point here, right. So, next is now what will be the maximum critical your clearing angle. In this case, for this kind of problem, what is the maximum your critical clearing angle delta CR. The critical clearing angle is reached when any further increases delta 1. That means, this delta 1, this is delta 1, it is increasing, right. What will be the maximum one? Increase in delta 1 causes the area A2, that means, this area A2 representing decelerating energy to become less than the area representing the acceleration energy. That means, if this delta 1 in this curve, if you look, if you delta 1 you increase, then this area A1 will increase. So, A2 will decrease, decelerating energy will decrease and this will increase. Finally, it will go to a point where A2 will be equal to A1. So, this is that this is the same graph, this is the black one, this is blue one and this is the green one, right. So, A graph is before fault, that is pre fault, and this is your this one after fault is cleared, after fault, and this is post fault, right. So, this is your during fault and this is post fault. So, in this case, suppose maximum we have gone up to delta CR. So, this is accelerating energy A1, this is A2 and this is delta M is equal to delta max. I have written here same thing, and delta max will be pi your for this graph, this is F and A. So, pi minus delta 0, sorry, it is this is blue graph, pi minus your delta M dash, right, because here this is the point, this is the point, this was actually the steady state operating point. Here I have not shown, here I have not shown, here I have not shown, this is a blue line, horizontal line and this one, right. So, this is actually, this is the area 1 must be equal to A2 and this is the maximum clearing angle. Thank you.